All right. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. So our class today is designed for manufacturing. There is the quite good topics. So there is a very interesting because we already learned about product architecture and then industrial design. So now we go for the design for manufacturing. So the FM. So this very important part in the manufacturing, because as a design engineer, we need to consider not only the design, like modular design, integrated design, what we learn in the architecture, and then the industrial design as well. So we need to know how to manufacture the product in terms of our design can reduce the cost, can give more quality in design. All right. So this very important because customer need and product specification are usually our guide in the concept phase. You learn already concept phase. There is the specification from that you use as a guide. Sorry, you use as guide to product development. And then you can see from this chart, start from planning. We do concept development, system level design, detail design, testing, and then product ramp-up. So in terms of this process later on in the testing and then product mass production. So later development activity like this often have difficulties to link need and specification to the specified design issue when the designer face it. So that's why we need to have this in earlier stage. For example, in the concept development, system level design, or in the detail design. So perhaps we can do in this one concept development phase. I put 1 star here. That means that less difficulties. And then when we go for the system level design, it's more difficult. And then more difficult in the detail design. So how can we emphasize manufacturing issue throughout the development process? So we will learn in next slide how to do it. From using the FM concept. So our outline for today's lecture is we will cover about the FM concept, the FM objective, method, manufacturing cost estimation. So this is very important because the cost, when we talk about product design, product manufacturing, so the design for manufacturing DFM, so they always relate to the cost. And then we do cost estimation, and then this one we relate with the effect, and then impact and example. So this is our outline today. And then manufacturing cost, like I said just now, is the key to determine of the success, economic success in the product development. So in simple term, economic success depend on the profit margin. In the profit margin, what we can earn on the sale of the product, and then how many units of the product that company can sell. That is very important. Profit margin, what we can earn after we sell the product. And then profit margin is a difference between the manufacturer selling price and the cost. And the cost of making. I believe you already learned in the manufacturing engineering before, the profits, revenue, total cost, and then fixed cost. So from there, you can do the calculation of the profit. So the numbers of units sold and the sale price are to large degree determined by overall overall quality of the product, overall quality of your product. And then economically successful design is therefore about ensuring high product quality, high quality while you minimizing the cost. So be careful when you do a cost cut down, minimize your cost. So you need to take care on your quality, product quality. So DFN is one method for achieving the effective method to achieving the low cost manufacturing, So without sacrifice any qualities issues. So the major objective we can simplify on for DFM is the reduce cost, reduce assembly cost, and then reduce production support cost. So when we do the design, of course we do for the component, and then after component we need to assemble. So both we can tackle for the reduced cost. All right. Okay, we go for the introduction. We have learn about we will learn about the design for X. Because DFN is part of DFX. And then this one, design for X is about quality, X about quality. So because DFX methodology where the X here correspondent to 1 dozen of quality criteria such as reliability, robustness, serviceability, environmental impact, and manufacturability. This right here is a manufacturability, so DFM. So the most common of this methodology is design to manufacture, design to manufacture, design for manufacturing, manufacturability, DFM, which is a universal important because it's directly address a manufacturing cost. So after we go for the DFM is part of DFX, we go for the cross-function team inside the DFM, and then perform through the development process. So these three we will cover today, and then I hope you can understand, you can relate with the what we learned previously, and then I think you also already learned as well in the manufacturing engineering. You can remember back the concurrent engineering, the what we call it, the process design and the manufacturing process as well, to relate with this topic today. All right, this chapter will discuss about DFM one, but it's also intended to illustrate. I will give also the example for general principle which apply to the methodology of achieving X, achieving X. So how to achieve the X? So we have a detailed design decision can have substantial impact on the product quality and cost. Number one. Number two is development team. Development team face multiple and often conflict goals. So this one also we need to achieve. And then it is important to have a metric which to compare alternative design. Here, alternative design. So dramatic improvement. Dramatic improvement often required substantial creative effort early in the process. So creative effort early in process. So a well-defined method assists the decision-making process. So all this one is a methodology for achieving the quality, DFX. And then for the cross-function team, cross-function design, design for manufacturing, DFM is one of the most integrative practice involved in the product development. So DFM utilize information of several types, including sketch, drawing, product specification and design alternative, details, understand of production and assembly process, estimate cost production, volume and ramp-up timing. And then this DFM required the contribution of the most member of the development team. So I think you still remember the concurrent engineering, like I said just now. So the concurrent engineering, we do parallels in various departments. So we cannot only concentrate in the design process by the engineer. So we need to concurrently with the others department have. So there is a cross-function team. So we need help from the productions, from the engineering side, even from the customer as well. So they give the valuable information to our design. So in the concurrent engineering, if you can do that, we can shorten our design lead time, because the pace of the process or the part always change very fast. So we need to react on that pace with what you call it, the drawing changings. We need to give the more efficient work. So when we design, we need to design the product that can be manufactured, that can be produced. We cannot design, because the designer always do the design. They need to have more information from the production side. For example, they design the tolerance, for example. So the tolerance itself, they need to know how to achieve it. So, for example, the designer cannot design with the tight tolerance. If they do that, the manufacturing don't have capable to produce. So they need to buy another tool. We need to use the sophisticated machine, for example. So they cannot achieve it. So that's why the designer need to see our capability in the production, either that specification need in purpose or just they build based on their theoretical in the textbook. So that's why when we design, we foresee the importance of the tolerance itself. The part what we design, for example, we need to have chamfer, for example. That chamfer is needed or not. Why important? So that's why we need to consider in earlier stage. And then when we work concurrently with the production side, we know their capabilities, we know their customer need. So we can integrate all this information inside our design. So the team DFM effort commonly draw by expertise from the manufacturing engineer, from cost accountants, production personnel, production engineering, like I said just now, even maintenance, and they will work together with the designer, product designer. So that is what we say cross-function team. And then many companies use this structure or use a structured teamwork base to facilitate the integration and share the view of required for DFM. So they do like this one, sketching, they do the drawing, they do the specification based on the customer need. And then they make compare with the alternative design what they have. And then they produce the detailed design that can be understood by production in manufacturing floor, the production floor. So the people inside, the operator inside can easily assemble, can process, can produce the drawing, the detailed product specification that what they highlight before. So this one, we can do also estimation of the cost in beginning. So we don't, we can estimate the production volume, the profit, the revenue what we can have after we sell this product, after the product get to the market, introduced to the market by mass production. So I already explained in my previous class in the manufacturing engineering. So this cross-function team or concurrent engineering is very important because one, pace of the market change, like I said just now. So when the pace market change increase, they need the fast reaction, fast action from the company, from the all bodies in the department to work faster. And then company must keep that pace with the changing, with the market changing, with the requirement changing, with the competitors. They need to keep the pace. And then decision made need to be faster. When they have this systematic cross-function team work together, they can make a fast decision. Whether we can produce or not, we can make a new design or not, although we can need to change or modify the drawing or not. So that is the fast decision we need to make during the process, design process. And then one more important part is reduced waste, rework waste. So that is also related to the quality, related to the X in the DFM, because when we reduce the waste, so we also reduce the rework of the part, the quality of the product. We can control, we can seize, and we can produce the high quality product. And then product can be quicker to deliver to the market. So we can design, we can produce, and then we can release to the market earlier. So that's why this is very important. And then company can operate more efficient with this method. So with this DFM cross-function team, we go for the DFM process. So this process, we have to estimate the manufacturing cost. We need to reduce the cost of component, cost of assembly, reduce the cost of supporting production, and then we need to consider the impact, of DFM decision on other factors. So we go for the number one, estimate the manufacturing cost. So manufacturing cost, very important part when we want to do the cost saving. We need to make estimation. So we need to know the cost occur inside our production first before we can go for the estimation purpose. So we need to understand the cost categories, estimate the cost for the standard part, estimate cost for the custom made part, and then cost for assembly, and then cost for overhead. So these all type costs we need to know well, and then we can do a estimation. So I believe this fixed cost, variable cost, you already learned, but I will explain later in next slide regarding this cost detail, how they can affect the manufacturing cost. And then estimate cost for standard part. Normally we do a comparison to the similar part using in our production or our product. So normally when we design a new product, so we have already the product run in our production line. So some that product use the standard part. So we can take that as an example to see the standard part design, the cost occur in that particular part. So we can get roughly the cost from that standard part used. Either we get quote from if the part is not available yet, we can get from the vendors. And then for the custom made part, so this one very related to the what material we use, how many hours, how many person we use to operate the machine, to change the material to the expected part. So the tool, jigs, fixture used, so how about their cost? So we can consider all this one to estimate the cost for the custom part. So this one also depend to the production volume. So of course, you learn already economy of scale production. So when we produce one, the cost is very high. So we need to think about to produce or to order more part to reduce the cost. When we order the, for example, when we produce more, we order a lot. We order in the bundle for the material, for example. And then fixed cost for the machine or toolings, because we buy a tools, we can produce a lot by that similar tooling. So this is related to the fixed cost as well. And then levels. Levels, normally the company hire them to work in the specific time. So when we utilize that time to produce more production, so we can cut the cost down, and then we can reduce the cost. So dependent to the production volume. So yeah, this one, when we think about the volume of the production, we can change this one to the standard part as well. So if we can produce in our production line, or we can make in-house, not depend to vendor anymore, we can change to the standard, company standard part. So this one also in the buy or produce decision, buy or make decision, based on the feasibility studies, we can judge whether we need to depend to our vendors or depend or we can produce in our facilities, using our facilities. So this is already covered in the previous topic in the manufacturing as well. And then estimate cost for assembly. So normally time by rate. So they use assembly operation by time rate. So normally when we produce the part to assemble, we do a time, make a production time using the cycle time. So one product to another product, we need to count, and then we can do a time studies, time analysis. So that is a cycle time. So from beginning until the end, product finish, we can take the time. So we call it as a time rates or cycle time. So they can estimate the time for the assembly by operation time. And then cost drive, cost drive or cost driver based on the overhead cost. So we will explain all this one in the next slide. So before we go there, so I will need to explain more on this DFM method by cost estimation. So we need to, when we have a proposed design, we need to do the estimate cost by this 3 section. So we need to reduce cost of component 1, and then number 2, we need to reduce the cost of assembly, and then number 3, we need to reduce cost of supporting production. These 3 costs we need to make estimations before, or we know what inside this ingredient inside this cost, and then we can make a reduction. So after that, we consider the impact. After we get all this information, we can make decision based on the impact we will face if we reduce this cost. So the decision on other factor also we will consider in this stage. And then after that, we recompute. We will calculate all the costs. After we reduce the cost, we can get a new cost here. We can make a final decision on this by recompute the manufacturing cost, and then we make a judgment. Judgment here, either we go for the acceptable or we accept all this drawing based on the cost, what we reduce, the component we reduce, the assembly style maybe we already reduce. So all this related to the cost and quality. So we need to accept in good enough or not, or we need to revise back. If no judgment here, no, we need go back, and then we need to see the each component again, each assembly line, each supporting production, and then we go through the same process until we satisfied with the drawing what we achieve. So this is all DIFFM method. So this one also relate to this this part. So I think this one you already know the total cost. I need to use pencil, sorry. So this total cost, okay, total cost equal variable cost multiplied by quantity plus by fixed cost. F is fixed cost. So this one I think you already know or learned in previous module. When we count the profit, profit, always revenue minus total cost. So total cost here is this one. Total cost, variable cost multiplied by quantity plus fixed cost. So from this graph, you can see this is total cost for the injection molding, TI. And then this one is total cost for machining. So this graph, they have a different line or starting point. So you can see there is a total cost for machining and then total cost for injection molding. So they have different here. For injection molding, you need to invest a lot of money before you can start your business. But for machining, you use less cost for starting, estimate like 1,000 here for the fixed cost. So the fixed cost is the investment you need to invest before you can start the production using that particular machine. So of course, the graph is plotted within the quantities. Quantities here, the x-axis is a number of the unit production produced in time. So you can see here when the molding, when you use the molding, even the starting cost is very high here. But when the quantities, when you achieve the quantities, the production goes on. So the cost not much change from the maximum one, just a little bit changes, increasing not so much. But for the machining, even though the start cost is less, 1,000, but they have rapidly increase the cost related to the production numbers of quantities. You can see here, there is the cost equal or increase rapidly highest during this production using machining based on the quantities. So from this chart, you can see that you can conclude that if you make investment for long term, for mass production or for target high volume of production, you need to use a injection molding, because the unit per cost here is $1 per unit. This become to $10 per unit. So based on the unit price. So that is how we can do this information for estimate the cost of the unit price component. Even we see that we use less capital investment at the beginning, but for unit cost, we lost already. But if we think for long term, we need to invest more on the injection molding, and then we can get $1 per unit material and processing fees for part. So that is how critical when we decide for the investment or not for new machine or new line or new productions inside our production. So this is very useful information when you design the proposed design here. We propose design here. We need to consider the assemblies or production. So these two parts, we can think the machines and what we want to use here, whether we need to use machining or we need to use injection molding. So we need to think also the quantities. If we have enough quantity, so we can go for the injection molding. But if not, we can still use machining. So you can see here at the intersection line here, they have a what I call it break even, when we can use whether change from machining to molding. So if 1,000, that is a break even quantity. If you have produced, you target to produce more than 1,000 units, your volume production, you need to go for the injection molding. So if less, you can use machining. That is how you can use this graph to predict when you need to change or need to buy to change the new machine, new process, new procedure. So the total unit cost here, so you have this one, this formula. So how to get this one? Because the total cost is a variable cost multiplied by quantity plus fixed cost. So you can get this one by using you need to divide by quantity here. All you need to divide by quantity, even for fixed cost. When you divide by quantity, this one is package, you can get the total cost per quantity here, total cost per unit, which is a variable cost plus variable cost only plus fixed cost, and fixed cost divided by quantity here. So this one is a fixed cost, because the setup cost plus tooling cost is the fixed cost. So divide by volume. Volume is a quantity plus variable time, variable cost. That is variable cost. So that is how you get this formula. Total unit cost equal to the setup cost plus tooling cost divided by volume. So this is a fixed cost divided by quantity plus by variable cost. So this is how you can predict, estimate to reduce the cost for component, assembly, and support cost for the production. So based on this, you can always use this the simple input-output model. This is simple output model for manufacturing system. I think you still remember this process in the manufacturing. You have a material input, and you have a manufacturing process, and then you have product as a output. So there is a manufacturing process. You learn in the introduction of manufacturing engineering. So you have a material input, go for manufacturing process. You done some process, and then you get a new product. So the process is the change raw material to others shape or others mass quantities or others form. So there is a process to change the raw material. So the inputs normally they have some price for that, but in the manufacturing process, you need to have value add with $1 more there. So that is the value added to the process. To change the material, you need money to change the material. So the material we change based on process, you value add to that material, and then you get the product with the more dollars. So that is the cost. From $1, value add with $3, you can get $4 there for the output. That is all a simple mathematics, a simple formula to describe the manufacturing cost. And then how to relate with this input-output model on the manufacturing system. So you still remember what is the manufacturing system? What is the manufacturing system? Manufacturing system consists several what? Manufacturing process. This one, manufacturing process. So several manufacturing process inside this station, or inside this cell, or inside this job shop. They have several processes. So they count together, we can get the system, manufacturing system. Manufacturing system is conceived with the several manufacturing process inside. So they did the value added job to add to change the material. So what the job they did, what the process they do? So they have a raw material here, they have a level, there is a value added. They have a equipment, they have information, they have tooling, they have energy, they have supply, they have service. So all this value added to the process. They do this thing to change the raw material coming. So raw material also as one input to the manufacturing system. All this considered as input to manufacturing system. But levels, equipments, information, tooling, there is input to the process itself. Value add to the process itself. So to change the raw material coming to another form as a finished good product. So when they do that, they release also not only product, but they also release waste. So we need to reduce waste to make more what I call it, cost saving in our production, because the waste also coming from material. So when we release waste, this waste also need to dispose to either to recycle place, to environment, landfill. So that one need to pay money as well. So there is a cost as well. So there is a cost. So more waste, more cost. Or inventory to keep the waste as well. The inventory to keep the finished good. So that one also the cost. So that is the cost you need to count as when this one you make estimations. You need to count all these costs together and then get total this one, total dollars here. All right. So normally, as a metric, the cost of production, the cost of product here, finished good, the company generally, the firm generally count as a manufacturing cost. They compute by not only single product produced, but they dividing by total manufacturing cost. Divide by total manufacturing cost for some period time. For example, annually, quarterly, or by batch production. They produce 100,000 or 1,000,000 units. So they divide by that cost to find the cost per unit. So normally we cannot count, make one part and then see the equipment, see the information, see the tooling. and then calculate the cost. So we cannot do that. We just run several period of time, like 1 year, quarterly, or batch production for 1 million that I said just now. And then after that, we make average for 1 unit. Use these formulas, total unit cost. All right. So I think you understand this one, because this one just review from previous knowledge. So the manufacturing cost, summaries again, this show that one way of categorizing the element of manufacturing cost. So under this scheme or this figure, you can see the unit manufacturing cost of product consists these 3 categories. They have a component, they have a, sorry. I need to change. Okay, I need to use this one. They have component, they have assembly, they have overhead. So these 3 costs, the major costs we need to know. For components, the cost for the component, they introduce, include with the standard and the custom that I introduced before. The component of the product, they may include the standard part, what we purchase from the suppliers, from the vendors. That is the standard part. And then we have also custom part. So the standard part like motors, screws, switch, electronic chips, so all considered as standard part. But custom part, we have raw material, processing, tooling. So when we order the standard, we need to calculate the material we use and the processing used in that process to change the raw material, and then the tool used as well. So there is a custom cost included in this component. And then for assembly cost, they have a discrete unit, goods, because we assembly one product, unit product. So I generally assemble from the part, So we have several parts, and then we assemble that part together. So the process of assembling almost equal or always use labors. So also we use machine to assemble, but the machine also operate by labors. If we use a fully automation machine as well, we need also labor to monitor, like specialists to monitor the machine. So we need labor to operate the equipment, tooling to assemble the part. So this one will equal the cost for the equipment and tooling. And then overhead cost. Overhead cost categorized use by support and indirect allocation. These two. So we will find it distinguish these two types by support and indirect. Because indirect we have overhead for factory overhead and corporate overhead. For support costs, we have for the cost for the material handling, quality insurance, purchasing, shipping, receiving, so facilities. So for indirect cost, in the textbook, I think you can refer the textbook. Indirect cost, they have overhead expenses like maintenance, security, material handling, shipping, heating, light, power for machineries, and then equipment, equipment utilities for the equipment. And then they have also corporate. So what is the corporate cost? So corporate cost consists with the like R&D activities. We have research development activities. That is also corporate. So corporate also consists with the marketing. We need to market our product. there is an indirect cost. Market our product. Because we manufacture the product, we need to sell the product. We do the marketing, we do the surveys. So that is also indirect. And then legal, we need to make agreement with the suppliers to buy component, to buy custom part, to make agreement with the outside vendors. We make agreement with the sellers. So all these agreement binding with the legal agreement. So we need to pay all this one under corporate. And then tax, insurance. So all this one under indirect cost. So this is overhead cost. So these three costs, component, assembly, and overhead, will contribute or will total up to become a manufacturing cost. So these just summaries from here. Just summaries from here. All this one, and then go for finished good. So this one summarize, you use component, assembly, overhead to get the price for the manufacturing cost. Okay, let's go for the fixed cost versus variable cost. Okay, sorry. So I think this one straightforward, because this one just revise what you learned in the previous module. So the fixed costs are those that occur on the predetermined amount, regardless how many unit of product are manufactured. So when you invest to buy a injection molding, for example, just now, how many unit manifold you produce by injection molding is not count. Even you use to produce 1 unit injection molding, for example, you need to pay the same thing. If you buy installment, you need to pay the installment until you finish. That is the fixed cost. So the fixed cost, regardless how many quantities you produce, the same. You need to pay the same. Even you not produce, you just buy for 1 month, you produce, and another month you not produce, not utilize that machine. You still need to pay the mortgage, the installment when you pay you buy the machine, or you rent. For example, in the fixed cost also for the buildings, you rent the building for your business. Even you cannot sell anything in that day, you need to pay the rental. So that is how the fixed cost count. Even you cannot make selling on that day, they also need to pay the cost for the renting. And then variable costs are those occur in the direct proportion to the numbers of units you produce. So that's why just now in the total cost, the variable cost multiplied by quantities. So depend to the quantities, you can get the total of the variable cost. So if you produce more, you need to pay more, or you need to have more variable cost. For example, the cost of raw material. If you want to produce 1 unit, you use less material, but if you produce 1,000 unit, million unit, you need to buy more material. But yet you need to think about the economy of scale production as well. So the unit of quantities, even when you produce less, normally expensive, than you produce more. So that is the relate to the quantities, the scale, economy of scale. But they always direct proportional to the how many production quantity you produce. Another is utilities, labors also. There is a variable cost, because they always relate to the quantities used to produce that particular part. All right. And then because of manufacturing cost estimate is fundamental in the DFM, so it's useful to keep this information well organized. You need to have this table to keep your all information organized. So the information here show you how to record the system, how to record the manufacturing cost estimate. So it consists of the bill of material. So all we call as a BOM. To pronounce the bill of material is BOM, but always people pronounce as a BOM. BOM. So that is a bill of material. So when you heard what is your BOM, you need to produce this one. Please show your BOM. This the estimation cost you need to produce or need to record, or you need to show to your marketing or your director to show the cost for your design, for your part you want to establish. So the BOM usually individuals list of each individual component of the product. So they create using the format like a tree structure here. So for example, they have a manifold, there is a part, and then this is the child part. Because the manifold made by casting, there is one part only. For using casting, there is the cost for the manifold. But for the EGR is for the, in the textbook, they refer to the exhaust gas recirculation part for the manifold. So the exhaust gas recirculation part will connect to the manifold. The part consists with the pipe, only pipe, because they use the pipe as a connector to the manifold. And then they assemble with the PCV assemblies. So PCV is the part also for the manifold to connect. They say there's a positive crankcase ventilation. There is a positive crankcase ventilation assemblies. They connect to ground, to bodies, throttle bodies, engine, and then manifold. There is a PCV assemblies. So you can refer back to textbook to this picture or this part explanation. But what we want to know is the part conceived for this PCV assembly. They have valve, gasket, cover, and screw. All this child part assembly will make a PCV. So they write down here cost for each part. Cost for each part in this BOM. And then they also have vacuum source block assemblies. So this consists with the block, gasket, and screw to produce this assembly part. So all this is related by tree structure. It's related by tree structure. From the manifold is the big part, and then to connect with that, they have a machining part for the manifold. We have a EGR, we have pipe, we have PCV, we have vacuum. So all this in the bill of material. So in this BOM also they divide by two columns. So the column for the variable cost and then fixed cost. So to produce the machine NIM part from the casting, they use also fixed cost. Fixed cost is to use a machining and to use the injection or what. So in this case, they use a machining for casting part. They get a casting product, this one, but they need to machine and they need to invest on buy machine to make more to achieve the specification from the using the machining. So need to machine the part. So the toolings, the lifetime toolings, this is total for the fixed cost, and then this is total for the variable cost. So others, they just using the standard part and the custom part, the purchase material and assemble the part, because this one assembly, but the pipe they just purchase, and then the labels for assemble in the manifold, they make a calculation here, and then this total variable cost. So same to the PCV and then the vacuum, they have a assembly cost for the label. So this is how they calculate all these total costs and feed costs. So on top of that, they also have overhead costs, overhead charge here. So overhead charge here, I will explain, and then we come back with the this figure later on to show you. But I will say that on top of that, we have a overhead cost here for purchase, for the processing levels, for assemblies, and then of course for the feed cost also they have overhead charge here. Then total on all of that, they have a overall the total cost for this part manifold. They have a total cost here. All right. So the total cost of the standard component are estimated by either compare each part to the substantial similar part in the firm. They use this part in the similar process in the company. So they have already used in the production, in the producing the part. So they already purchased that part. So they can make comparison, they make a reference to that part. So this easy one to compare the standard part they use. But number two, we need to soliciting the price from the vendors or suppliers. So we need to get the quotation, ask the price from them, so we can have the cost. So the cost of the minor component like bolts, spring, insert, so that is considered as a standard part. So we can use the similar component. Normally the company will buy in the bulk for that part. So the cost for the major part, major component will obtain by vendor or suppliers. So the estimated production quantity very important here. So for example, the unit price to purchase the screw, for example, as standard part, 10 times higher than if you purchase smaller amount. So if you buy a dozen screw, for example, that is 10 times higher than you buy 100,000 or 1 million screws, for example, per each month or each year. So that is how we can make anticipate the production volume quantity is very important to see the quantities we want to produce or we want to order, and then we can order in bulk for the standard part, or we can see for the custom part as well as a standard part if we have enough quantity. And for internally fabrication, if we have internal fabricate a standard component, if we also require the high quantity, if we want to decide to make in-house product or in-house production, we need to have a highest quantities to produce. If not, we better to buy from outside. For example, we already invest the feed cost. I cannot write here, sorry. Never mind. I will explain because I cannot use marker here. Or I can use this one. Okay, I use this one. Okay, I can use this one. So if we want to decide either we want to buy outside or we will produce, so there is a buy or make decision. So when we have investment for feed cost, for example, so we already have a feed cost for one machine in our line is $2, for example, per unit. This one I count already for $2 per unit, for example. There is fixed cost. So when we get quote from vendor outside, for example, one part is $10. But we already have our fixed cost for the machine, $2. And then we have also pay or delivers cost is $2 inside. So they have $4 already inside our overhead, overhead in the company chart. But we will get the quote from the vendor, they give us $10 a part. So when we make a feasibility studies to produce this part using this fixed cost, using these levels, we get $12 price for inclusive the material, inclusive the utilities, inclusive the variable cost, everything, we need $12. So from vendor, we get only $10 from vendors, the same part. So this, what you think? You need to order from vendor or you need to fabricate? Because fabricate $12, from vendor $10. So how you decide this one? So in this case, definitely you think about, oh, the vendor give $10, so there is cheaper enough, because we need to fabricate with the $12. We need to have more money in terms of fabricating ourselves. So we just leave it to vendor do it. But that thinking is wrong, because when you buy from vendors $10, you need to pay this one as well. Remember, this is a fixed cost that regardless the quantities you produce or not, you need to pay your workers or machine you purchase or invest before, because that machine already available in your factory, but you not utilize it. So you need to pay. So on top of $10, you need to plus $2 plus $2. So the cost from the vendor actually not 10, but $14. So this is much cheaper than $12. So the $12 much cheaper than $14. So you need to decide in that way. You need to think in that way. So even you get rotation $10 from vendor, so now this machine useless already. Because the vendor supply, you use the vendor, the machine not used. So in this case, as an engineer, you need to make a decision whether to buy inside or to purchase outside based on the feasibility studies. That is very important. You understand the fixed cost and variable cost, and then also to have some studies on your capabilities to doing it. Because even you have machine, but you don't have capabilities to handle the machine to produce using that machine, also useless as well. So you need to understand that by that particular machine, you can have enough knowledge to produce, enough capabilities to do it. So you can save your money, $12 by fabricate in-house. Yet, remember, this is long-term planning. Because when you think about fabrication in-house, in company, of course, you anticipate your production values more than that. If you think you want to produce one of 10 product only, so that is better you buy from the vendor. Because $10 is good enough for the 10 unit, because the quantity is less. So you can make this break-even chart. Just now, you can do the calculation using the break-even chart. You can see that. You can see that here. the intersection between this one, the 100,000, the 1,000 unit is the break-even volume. So you can make an analysis the volume here. The best volume you can decide whether you want to buy inside or purchase or to do it by your own. So just now here, yes, here. All right. I think this one, okay, estimate the cost assembly. Oh, feed cost, yeah. Okay. All right. So that is how you make a decision whether you want to buy outside or produce by your own based on this one. And then we go for this one I already explained, BOM just now. So estimate the cost of the standard component. So you need to make a comparison and then get a quote from the vendor by using that one just now. And then after that, estimate the cost of the custom component. So custom component normally based on the raw materials and then the products, the label what we have. So the custom component, which are part design, especially for the product, are made by the manufacturer or by the suppliers. So most custom components are produced using the same type of a production process as a standard component. So example, they have injection molding, stamping, machining. And then, however, the custom part are typical special purpose part, special purpose part. So the special purpose part, they're useful only in the particular manufacturer product. That's why they need customized. And then when the custom component is a single part, we estimate it cost by adding up a cost of the raw material, processing, and tooling. So we need to estimate based on this raw material, processing, and tooling for the each custom component or part. Okay. For example, here, cost estimate for the original intake manifold. Just now we use a manifold as a example here in the textbook. This one also you can find in the textbook. We have processing cost for the casting and machining reflect that cost for the complete casting line and several machining stations. So we have a variable cost for this one, and then also fixed cost for the machine that part. So the total cost on top of that, that we have overhead charge. So there is the total cost. So there is total cost for the custom part. Where we buy, we need to have another process on that. So we need to estimate all the costs for the variable cost and fixed cost together to get the total unit cost. And then estimate cost for the assembly. So the product made from the 2 part or 3 part or more than 1 part, they need to assemble. They need to assemble together. For the product made in quantities less than several 100,000 units per year, for example, this assemble is almost always performed manually because the quantity, because they use only can perform by job shop production, for example, by lot production, batch production. So you learn already that one. So they cannot perform automation to invest because the quantity is not enough to invest in the new machine. So they perform manually. So one exception of this generalization in this assemble for the electronic circuit board. So even the quantity is small, always the electronic circuit board using automatic machine or automatic line production, because they use a specific machine to produce the circuit board. So the quantity there maybe small, but they need to use that particular machine. We cannot do a soldering one by one for maybe one for 2 unit, okay, but if we 100,000 unit or 1,000 unit, we need a specific machine to do it. So there is even relatively to low volume, so we need to consider the automatic production for the electronic circuit. And then manual assembly cost can be estimated by summing the estimate time of each assembly operation and multiply by the level rate. So we can get the assembly cost. So assembly operation required from the 4 seconds to 60 seconds each. Depend to product, I think, because some product may be more than that, but depend upon the size, depend on the part. So the difficulty of the operation also, and then the product quantity. So we need to think, we need to calculate the assembly cost. All right. And then at high volumes, a worker can specialize in the particular set of operation with the special jig features, tools can assist for this assembly. So when we want to estimate the assembly cost, we need to make a line balancing or line take time for the time studies for the assembly process. So we need to count the time from the beginning until the end, and then we need to have 1 unit time for each product. For example, in this case, when we do the assemblies, valve, ring, spring, covers for PCV, valve just now. So we use this component and then we need to assemble. So the total time to assemble is 31.7. When we make a measurement in the time taken in the line, that is the time in the second we take. And then after we make a calculation, because the assembly cost for 1 hour is $45 here. So $45 for 1 hour, 60 multiplied by 60 seconds. So you can get this total time for the 31.7 seconds. You can get this time. So this is $0.4. So that is how we can get the cost for the time. We get the time, and then we can, from that time, we can estimate the cost for the assemblies. All right. So we go for the next is estimate cost for the overhead. Estimating the overhead cost. So accurately estimating overhead cost for the new product is very difficult. It's very difficult because the industry practice are not very satisfied with this one. We just different practice, different cost. So we will describe the standard industry practice here, and then identify some of their problem. So the applying the overhead estimate scheme used by most firm or company, very simple. They just estimate the actual overhead cost incurred by the firm or company due to the particular product. And then the indirect cost of the supporting production are very difficult to track. for indirect cost, like marketing, for example. We cannot say this marketing for this particular product, because when company did that one, they just do it based on the company profile, company lump sum. So they just go for the overall. So very difficult to trace, track, and then assign to the particular production line or production or particular product. So we cannot do that. So the future costs of the supporting production are even more difficult to predict, because the future costs, like a new product, we doesn't know yet. So that's why we just use the existing, or we have some track record previously. We just use this one, but we discuss this one further. So the most firm assign, how they do it, the most firm they assign overhead charge by using overhead rate. Some company just using some rate, a percentage. They call that as a burden rate. So they use that burden rate as a overhead charge. So overhead rates are typically applied to one or two cost drivers. Cost drivers are parameters of the product that are directly measured. So these overhead charge are added to each direct cost in proportion to these drivers. So the common cost drivers are the cost of any, like purchase material. They add the percentage on that, on the purchase material. The assembly levels, they multiply on top of that, and the number of our equipment, the time using for the product consumed, they also apply on top of that. So for the example of the overhead rate, the purchase material might be 10%. They decide 10% or 5%. So that might be the rate, the percentage they decide. Then the overhead rate for the assembly level might be 80%. So they have different rate for purchase, for labels. So they will decide. So each company, they practice different way, but always they have a track record before. And they have from the track record before they make a estimation, they make forecast, they make decide their own parameters, the burden rate, that one. So of course the purchase components already have they already include in the vendors, but on top of that, they also need to add on that one as the company burden rate as well, because company we prepares the letters to request the what we call it, the price from the vendors. So to follow up, to call the vendor when the product will come. So all that one considered as the cost. So on top of that, they also have overhead cost, even they purchase from the vendors. All right. So this one, I will show you. I will go back to this one. Yeah. So when you have this one, overhead charge, there is the burden rate here. For purchase material, they already purchased from the supplier, for example, the material. There is the total cost, but the overhead cost still 2.6 here. So that is what we call it the rate. On top of this one, they have some formula to calculate. They have this rate for this one. And then for the machining level, for example. On top of this one, they have 9.42. Maybe 80% from this one, they have this one. And then assemblies, they have on top of this one, they have overcharge the overhead charge for each driver, purchasing, level, assemblies, even for fixed cost as well they have. So that is how they do it, this one. All right. All right. We go for the number 2. Reduce the cost of component. Reduce a cost of component. We need to understand the process constraint to the cost driver. So some component part may be costly because the design did not understand the capabilities. Like I said just now, the designer should work and should know the capabilities of our production line. So this one very constrained to the production process. For example, the designer maybe specify the small internal corner radius. For example, they have a part. They have part like this. Instead of doing this one, they make a sample here, like this. So this is radius corners, for example. So the designer need to know why they require this one. If this one actually needed, or just they do it without know the purpose. So in the production, they means everything in production side. When they get the drawing, when they see this one, they mean the radius chamfer. They need to use a machining part to realize that physical part by creating that one. They need expensive, for example, EDM machine, electrode discharge machine, to do that operation. So they need that specific machine. So the designer may need to understand why they need this one, need that tolerance. So the designer may specific dimension, the tolerance, what they have, what they need. So the difficult tolerance, the difficult specification, difficult to achieve by accuracy with existing machine, they need to avoid that. They need to think how to produce it. To do this, the design engineer need to know what type of operation, what they have. Like I said just now, concurrent engineering. They need to work together with the production floors to know the capabilities, to know, to get the input from the production. So that is how we can reduce the cost of the component by identify the process, the constraint drivers. And then some part need to be redesign component to eliminate that process system. So when we see that radius doesn't need, we need to redesign that process. But even some production, they have the numbers, the step for production. So reducing the numbers of step in the part of fabrication process will generally will reduce the cost as well. Some process step may be not need. They just having this step from generation to generation. So when the new engineer comes, they ask you, what purpose of this step? What purpose of this production? So they say, doesn't know. So what if we eliminate that step? What happened? So they said nothing happened. So eliminate. So we can reduce that cost. So that is how we work. We make a process simple. For example, aluminum part, they already, because we use aluminum, no rusty already. So the part is not pain. It's not pain, especially when they visible, not visible to the users. So for example, inside. So when you open some part, when you purchase some part, when you open, they not paint inside, because there is already reduction of eliminate the process of painting. You can reduce cost on the painting material as well, the process. So that is how we know the step, the process. We can reduce, we can eliminate the step, the process of the painting, because they're not visible to the users of the product. In some case, Several steps may be eliminated through substitution of the alternative process step. So we can eliminate the step if we combine this step with another step, with another alternative step. So that is how we think when we go to see the production. Even we can use, oh, this one we can eliminate if we use a net shape production, net shape process, for example. What is the net shape process? Net shape process is like casting, like forging, like extraction. So we use that process, we have a final geometry, intended geometry in the single manufacturing step production. We just casting, and then you get a shape there. You extrude the product, and then you get the totally the one form of product look like as your design already. So there is you can reduce the step with alternative process. But yet you need to think, you need to remember that all the process cannot be casting, cannot be used as a forging. So some process can, but you need to make a studies on that, detailed study on that, to find out either you can use casting, forging, extraction to replace the existing process. Okay. And then the manufacturing cost of the product usually drop as the volume increase. So this phenomenon is labeled as economy of scale, like we talked just now. So when we can produce more, we can reduce our cost in terms of economy of scale. Economy of scale for fabricated component occur in two reasons. Because of the fixed cost, divide amount the more unit. So remember, when you invest with the fixed cost, you buy, even you produce 1 or you produce 1,000, the cost you need to pay. But if you produce more, you divide by that more product you produce, you can get relatively small for unit product. You remember, unit product is divided by quantities. So the fixed cost divide by quantities, like machine, like tooling, you divide by quantities plus variable cost. So variable cost already get from volume already. So that is how you can use economy of scale for fabricated component occur in your production line. So you can have a fixed cost by dividing among more unit. And number two is a variable cost become lower because the firm just use the larger, more efficient process and equipment. When you think about economy of scale, even you use variable cost multiplied by quantity, the more quantity you produce, more variable cost. But in terms of the more efficiency process and equipment use, that is very sufficient enough or good enough to see that the economy of scale in terms of using variable cost for the amounts, the large amount of the operation or process. And then the principle of economy of scale just now also apply to the selection of component and the process. Selection of the component of the process. So the production volume increase. The production volume of the component increase. So the unit of cost of the component also decrease. So there is an economy of scale. And then the quantity performance often increase as well with increasing production quantity because the producer of the component can invest in learning, improvement of the component design and its production process. Forgiven the expected production volume just now, the high volume, the benefit of the sustainability, higher component volume can be achieved through the use as standard component as well in their process. So when we think about that, we find out the standard component, we can relatively achieve the cost reduction. And then the component of cost reduction strategy also use this black box component. There is an effective strategy in the Japanese automotive industry. They use this black box component supplier. So what is the black box? So black box is the one approach to the supplier when they want to order something, order the component. They just describe the component, not what the component, what they want. They just decide what the component has to do. What the component has to do. The component is for what? For what? What? That is the description they write in the request. What this component is for what? For this, for this, for this, for doing this. Not how to achieve it. Some practice from the company. They don't use this one. They just call the vendor. They said they want to have this one and want to have this cup. They just exactly say that this what they want. But in Japanese practice, they don't say they don't want this cup. They want something used for drink, the cup. They just describe what that component can do, what for. So the company, when they receive the instruction, receive the order from the company or their supplier, they can easily understand. They just decide the specification to the vendor because they just want the part, the component. So they give the wide possible latitude to design or to select the component with minimum cost. So when we decide they want to like this, exactly like this, the vendor will find out like this, so the cost very expensive. But if you say you want just something to drink, they can propose to you 3 or type of cup, maybe like this, maybe like this. So you have 2 different choice with the black box component request just now. So because you don't set specific what type, so but all can do for use for your drink. So you can say that this one how much, this one how much, what this one, yeah, the specification of this one. So you can decide. Or for us, we don't need this type of cup. We need the simple one. So this one very cheap. This one $10. This one $20. So you take this one. So that is how we use a black box component in our reduction cost of component. So this all you can apply, you can use to reduce the cost of component in your manufacturing cost saving. All right. Okay. We go for reduction cost for assembly. So design for assemblies, because when we manufacture, like I said just now, when we have one or more component, and we need to assemble, for example. So we need to think about design for assemble. So DFA is a fairly well-established subset of the FM method. So one part of subset for the DFM, actually, DFA. So that involved with minimizing the cost for assembly. So when we think for the cost saving, we need to think for design for assembly to think cost reduction as well. Because in our chart just now, oh sorry, This one, I go back. Yeah. So in the manufacturing cost, they have this one, assemblies. So this one, we need to consider to reduce the cost using the FA method. So for most product, assembly contribute a relatively small fraction of the total cost. Okay. So the integrated number one, you can see integrated part do not have to be assembled. So you learn inside the product architecture, the two chunks combined together, we can get integrated part, for example, in the design. No need to assemble. So that they have effect the assemble of the geometric features of the part. So they accomplish in the fabrication process already. So the integrated part often less expensive, but we learn in the product architecture, the integrated part is expensive. But some case, so in come for this design for assembly, you can think, different way for this one, because some integrated part are often less expensive to fabricate than separate part they replace. Because with this availability of the machine, tooling what we have, we can fabricate using the rapid, what I call it, the additive manufacturing, 3D manufacturing. So we can less expensive to fabricate rather than you use a separate part. The cost may be more or less similar right now, but we can, on top of that, we need to assemble the part. So that is the separate part. So we need to replace the separate part by thinking integrated part fabrication using this both method. So when we use that one, we can design, we can use mold, we can use temper, or we can use the casting part. So this is, yet you need to remember the quantities. So the quantities should be there. So you can have a cost saving occur because the single complex mold or die using in this process usually less expensive than two or more less complex mold or die, and because there is usually less processing time, and then using this integrated part. So integrated parts allow the relation among critical geometry features. So when you use integrated part, they already think about critical geometries. You don't need to fabricate, to machine, to produce that one, because in the single process you can produce the geometric features to be controlled by the part in this process. So if you think about assemble, so the critical part for the geometric features also you need to assemble well. Some is very difficult to assemble to get the precise control on that part when you assemble. But when you use a molding to make that part, so the geometric, the critical features already control one single manufacturing process already. And then part number two, part is insert from the top of the assemblies. So this attribute of the part assemble is called Z axis. So normally when you push from the top, they use what I call it, the gravity help to stabilize the partial assemble. So you just leave it and then just make the part self-assemble. So they can maximize easily assemble to this part. So you need to think about that to design for the assembly part. And then assembly worker can generally just doing the part alignment, for example. So when the part that require fine positioning in order to be assembled, they require a slow process. The operator need the fine tune. They require a slow process to precise the moment on the part that assembled by worker. So part and assembly site can be designed to be self-alignment, so they can be fixed. So some part need to what you call it, fine tune by workers. So there is required long time to to assemble. So the most common self-alignment feature is the chamfers. So when we design the part, instead of this one, for example, when you design the part and then you have another part to put inside this one, for example, like this. So the chamfer here will interrupt you to make a size alignment. So normally we will design inside this one, they have a like this chamfer. Sorry, I use different color. So this one, the cut. Oh, sorry. So this one, your design the straight no chamfer. So when we insert something inside this one, they need the self alignment to make the part be inside this hole. So you need to have a chamfer here, chamfer here. So when this one have the part will go through and then make a self alignment inside this part. So they need the orientation, and they just can be such what you call it, self alignment by themselves. The operator just guide, the worker just guide, and then do some fitting. And then number 3 is do it yourself. Consider customer assemblies. So customer may tolerate completing some what I call it, the product assembled by themselves, especially if doing some technical product, technology-driven product. So nowadays, when we buy something, they have do-it-yourself. We need to have the product already half assembled. We need to assemble by our own. When we buy some machinery product, when technology product, but they have instruction there. We need to have fun to assemble. So this one also quite good approach. So can reduce the cost of assembly as well. So we normally in design, we consider this half assemblies, and then we let the customer do it another half by doing your self approach. And then reduce, number 4, reduce costs by supporting production. So in working to minimize the cost of component and cost of assembly, the team may also achieve a reduction in the demand place of the production support function. For example, a reduction in the number of parts, reduce the demand on inventory management, for example. So you learn in the what you call it, lean manufacturing, in the manufacturing engineering. So when you use you have to assemble more product, you need the place, so you need the inventory. So inventory is the waste. Inventory is the waste. So you need to reduce the inventory, so you can reduce the waste. The reduction of assembly content reduce the numbers of workers, so they also can reflect to the numbers of workers, reflect to the numbers of the what I call it, material, human resource. So that is all reflect to the cost saving. So Standardization of the components also can reduce the demand on engineering support. So engineering support for the quality, for example. So they also can reduce on that to manage the staff, manage the inventory. So these are include for the support to the production. So by this they can minimize minimize the systematic complexity, such as plastic injection molding for one step of making a complex product. So that like extremely simple manufacturing system, for example, would utilize a single process to transform the single raw material, like we said just now, in the casting, in the extraction process also, or forging also. We can use this single process to have a complex geometry. So with this one, we can get a quality product. So from there, we can use more. We can use less supporting staff to monitor the quality of product, monitor the machine of the because they have a single process only. So the single diameter or the plastic, for example, we have to make one part, one rod, for example, using the extruding machine. So with single extrude, we can get the single diameter of plastic rod. For example, with the plastic pellet, we put the plastic pellet and then we extrude that one, and then we get the plastic rod. So with the single process, we can transform the complex geometry with the simple with the one process. So complexity arises from the variety in the input, output, and the transformation process. Maybe a real manufacturing process, manufacturing system involve 100 suppliers or 1,000 different parts to produce that one. So they have a different type of production process as well. So each people, each supplier, each part involved in the one in the complexity product or system maybe can be need to be monitored, managed, need to be inspect, handle, need to have inventory. So this one can be reduced by using the single production like casting I said, or extraction I said just now. So we no need to have more process, more space, more inventory, more raw material to fabricate, to get that complex product by several manufacturing process. So of course the quality control also very difficult to handle. So if production, they have need to check the quality for the each geometry. So by this single process, you can minimize throughout this production, one production only. And then number 2 is error proving. So error proving is an important aspect in the DFM to anticipate the possible failure, mode in the production system, and then to take the corrective action or measure, corrective action earlier in the development process. And then one type of the failure mode may be erased from the having slightly different part that can be easily confused, for example. So that is a Pokayo system. We need to make, in Japan, they use a Pokayo system to prevent the mistake in the production line. Because the production line, they rely to human, they just assemble maybe they don't know, for example, the screw, they have a pitch rate, for example, 4.7 millimeters with this 4.75 mm, for example. They have different little bit for the screws. When they have missing together, very difficult to differentiate. So that is how we need to have a foolproof system to make sure this can be detect which one the different for right screws for right operation. So we need to think about that to make our foolproof jig to prevent in the Pokayo system. So we can see also the direction of the screw. They have turning different left and right. So the product also they have a mirror image. So the part different based on that. So we need to differentiate using the error proof to anticipate possible failures during production system. So this also can reduce cost of the supporting production, because this one, the monitor the qualities, the review also the cost. So we can reduce all this one by reduction cost of supporting production. And then we go for number 5. After we have these 3, we have estimate the cost. We have reduction the cost of component. We go already cost for assembly. We go for the supporting production just now, and then we come here now. Consider the impact of the FM decision on other factors. So we need to consider all these reduction costs and also other factors before we make decision. Okay. So number 5 is consider impact of the decision. So in the economic success of the product also depend on the quality. Depend on the quality of the product. Depend on the quality of the product. Depend on the timelines of the product introduction, and then cost of the developing of the product. So the development of time, development of cost, product qualities, and then external factors such as component reuse and recycle life cycle cost is very important when you make a think about considering the impact in the DFN decision. So the development time can be very precise. So the automotive development project, for example, they have a time maybe worth as much for the $100,000 per day, for example. So for this reason, the FM decision must be evaluated for their impact on the development time, as well as their impact on the manufacturing cost. So while saving $1 of cost for manifold just now, so we can have a saving $1. So that is worth when we produce 1 million manifold per year, perhaps we can reduce $1 million annually. The cost saving, that is how we think. Even $1, but perhaps we need to think about the yearlies of the cost saving. And then development for cost, development cost closely mirrors to this development time. So the same caution about the relationship between part complexity just now, part complexity and development time apply to this development cost. And then before we proceed with the FM decision, the team members, the engineers should evaluate the impact of the decision on the product quality as well. So under ideal circumstance, action to decrease manufacturing cost, would be also improve the product quality. That is one important part. Even we reduce the cost, the quality should not decrease. The quality should improve or increase the product quality. For example, the manifold just now, when we reduce the cost, for sure we reduce their weight reduction, improve the engine performance. So this is how we think about new manifold design. Instead of we reduce the cost, we can increase the product performance and qualities. Okay, so it's not uncommon for DFM focus primarily on the manufacturing cost reduction to result the improve in the like easy dismantle, easy recycling. So from this one, we think about all. So when we think about that one, easy to maintain, easy to service, easy to manufacture. So we go for the product quality. And then design decision may have implication beyond the responsibility of the single development team. So in this economic term, this implication may be viewed as externalities, external factors. They think about the component of reuse, for example, component of reuse. So the time taking, the money to create a low cost component may be valuables, and then the design of similar product. So the thinking of component reuse is very important, not only for the environment's effect, but for the material itself. So we can reduce more cost when we promote this component reuse. And then life cycle cost also. Through this life cycle, certain product may incur some company or social costs that are not accounted for the manufacturing cost. So the life cycle cost also need to consider as an external factor when we consider to make decision on the implementation of the FM method. And then in conclusion, because we already cover all the DFM just now, so one part, in the introduction, we said that DFM, DFX also include in one part of the DFM. So design for X is a DFX. So I already summarized here. So the several based on DFX principle. So that is all related to the qualities, but contribute to the cost reduction. Because when we think about this one, we need to consider the impact of the DFN based on product quality. So the product qualities, they have several principles. You can remember based on the part shape strategy. Just now we already discussed this one. When you make a part, you design something, you need to specific process design guideline. If part symmetry is not possible, make part very asymmetrical, design pair part instead of right left. So if you make a pair, if confusion is not there, so you already have a good part already in line. So design part with the chamfers, avoid the confusion during the production, self-alignment in the public assemblies. So there is a part shape strategies. And then they have another standardization strategies, use standard part, standard features, and combine the part and the function. There is all standardization. And then we have assembly strategy just now. So assemblies for DFAs. So we need to think about the design product so that the subsequent part can be added to foundation part, design foundation part, so that is features that allow to be quickly and accurate position, and design product so part are assembled from above, from the top, using the gravity features to easily assemble, and then minimize the number of direction, and then so on and so forth. And then you have a fastening strategies as well. So using the minimum number of total fasteners, using avoid the difficult process, using the easily clip-on fasteners, using the special proper tolerance for the fresh peak. And then you have also assembly motion strategies. So fasten part are located before fastener is applied. So assembly motion are simple. Assembly motion can be done with one hand or robot. So that is all assembly motion strategy you can read here. And then you can read also automation handling strategies. When you use automation, you need to think about design, the select part can be oriented by automation, design part as easy maintained, using part that will not tangle when handled in a bar, use part what will not singly when fed and avoid this. So use part that not adhere to the each others on the track. Specific tolerance tight enough, automatic handling, avoid flexibility part which are hard for the automation and harder. So there is automation strategy. You can read all this one. We also have a quality and test strategies. For quality product can be tested to ensure the design quality. Testing can be performed by standard test instruments. So all this contribute the quality test strategies. And then the FM maintenance strategy. So easy to maintain, easy to open, easy to maintenance free, for example. All this one are the maintenance strategies. And then there are a lot of maintenance. You can go through this one. And then we also have not touched this one, but you can read this one in the textbook as well. Axiomatic design by Namsus, axiomatic design by Corollarius. So they have this different thinking principle for design for X. So you can use this one. And then, this one also they have the FA method for Boutros, DeVos, 3 categories. So all this one contribute for design for X. And then design for assembly rules, they have this rule. The ideas, the key ideas for the FA, for conclude, we have a minimize to part count, maximize the handling, easy handling, maximize the easy inserting. So all this one key idea for DFA, and then benefits, low cost, low labor cost, direct benefits. So this one you can refer for this one, but I not go through for this one because we just knows the just general for the DFA should be enough for this design for manufacturing. And then method for integrations. So you need you have a several method in the part integration. You need to always ask the candidate design, does the part need to move? Does it need to be different material? Does need to be separate? So I think also you learn the Scamper checklist in the manufacturing engineering, in the idea generation, for example. in the scamper checklist, you need to always ask the new idea. That part can be substituted with another part, or this material or this process can be combined with another process, or can adapt, can modify, can put to another use, or can eliminate. Each step can eliminate or not. So rearrange, either we can rearrange the process. All these the scamper checklist idea generation. So this method, instead of this one, you can also use scamper to find out the idea. So that is the method part for integration. And then 3 method to implement the FM, organization, design rule, CAD tools. So this one you can use, can understand the strategies for the DFM. So for this lecture today, we come to the conclusion. So for the summaries, DFM begin with the concept development phase and system level design phase. DFM utilize estimates of manufacturing cost to guide the prioritized cost reduction and effort, cost estimation required, expertise with the relevant production process. And then since accurate cost estimation is very difficult, so much of the FM practice involve making informed decision. So component costs are reduced by understanding what drive this cost and what drive this cost. So you need to understand that one. And then assembly costs can be reduced by follow well-established DFA guideline. So a reduction of the manufacturing support cost begin with the understanding of the driver of the complexity of production process. And then DFM is an integrative method taking place throughout the development process and required input from the team. And then DFM decision can be affect product development lead time, product development cost, and product quality. So I think that's all for today's lecture. So the beginning part, before I close to open to the Q&A. So the important part is only to see this process, because we have this DFM process. We go this estimate manufacturing cost, reduction of the cost component, cost assembly, cost of support production, consider. So this is 5 DFM process. So the process is very important. When you understand this one, is good enough already. And then if you want the what I call it, the additional information for like in the previous the last slide, we put some Bottroff method. You can go and then can read about that, so you can find more information on that. But the most important, when you understand all these 5, you can already understand everything about the FM process. You can use this knowledge to design, to think about the design for manufacturing. So that's all for class today. Thank you very much. Any question?